Okay, so we're going to talk about simple harmonic motion. We're going to define what it is and look at a couple of examples of when objects are actually moving through what we define to be simple harmonic motion. And the easiest way to do it is just to draw an example of it. So here I've got some horizontal surface, and here's a wall that's anchored. And what I'm going to do is I've got a spring, and then I'm going to connect this to a mass. I'm not drawing this very well, but oh well. And here's our little crate. It has a certain mass, and we connect it with a spring that has a certain spring constant. And you have to remember what a spring constant is. Spring constant tells you how stiff the spring is. Like if you were to stretch it or compress it 1 meter, how much force would you need? So it's the force needed per meter of stretch or compression. And springs vary tremendously. You know, the spring constant, depends on the problem you're given. Now, if you might recall that, well, let's just say that right here, if I'm going to put the object right here, and right here at what I'm going to define to be 0, and I'm going to call this the x-axis right here. This, we're going to put 0 at the equilibrium position. And the equilibrium position what does that mean? Well, it means that the force of the spring, and I'm just going to call that F sub S. I don't want to write the whole word spring out. Is equal to 0 at the equilibrium position. So I pull this thing where the object is not being pulled to the left or pushed to the right by the spring. Okay, and it'll just sit there. There's no energy stored in that system, right? The spring isn't compressed. You have no elastic potential energy. It's not moving yet, so it has no kinetic energy. There is no mechanical energy if it's just sitting there. It's a very, very boring situation. But if I were to take this object and pull it this way, so I'm gonna redraw it. Here's X again. Here's 0. Here's my crate. Sorry, making you redraw all this stuff. But what if I pull it out this way? And I'm just going to hold it there. Well, this is 0. This is my maximum X. And I'm going to call this A for amplitude. That's the maximum that's the maximum displacement from equilibrium position. Okay, sorry, I'll screen a little bit. So the spring is now stretched all the way out to here, and I'm holding it. Now, what's true about the force that the spring is exerting on our mass? Well, we have to remember the equation for the force of a spring. The force that a spring applies is equal to, well, first of all, it's proportional to how far I bring it out. X. But it's in the opposite direction of X. If my X is positive, the direction of my force will be negative. Does that make sense to everybody? Okay, if you fade it out, fade back in right now. This is a key idea. If I pull this out this way, my delta X is positive, but the force is negative. So the force the spring applies is going to be in the negative direction. And the amount of force depends on the spring constant. So here's our Hooke's law equation. The force of a spring is equal to our position, x, but in the opposite direction, times k, the spring constant, in newtons per meter. And again, this is a measure of how stiff the spring is. Now, what would happen, though, if the object were over here? Well, now, what's true about delta x? Now my position from the equilibrium position, my x value is negative. But what's the direction of the force? It's in a positive direction. So that means the force is in the opposite direction as x. And it's proportional. So so really what the force of the spring is trying to do, everybody listen, watch, think, okay? Because we don't have time, The force, do you see that the force of the spring is always trying to restore it back to zero, isn't it? Hey, look up here. I want to see your eyes so I know that you're looking at, you're seeing this. The force is always in the opposite direction as our position, and it's directly proportional to my position. In other words, if the force is twice as strong because I pull it twice as far away from the equilibrium position, well, then I'm going to have simple harmonic motion. So, if the restoring force, in this case the force of the spring, is proportional to the position, and assuming that zero is at the equilibrium position, but in the opposite direction, then we have simple harmonic motion. And the consequence of that is going to be that it's going to draw a sine wave or a cosine wave. It's going to look, if you were to describe the position or the velocity or the acceleration of this as a function of time, you're going to get a sine or a cosine wave. And we're going to discuss that later. You don't need to know that for this assignment. But I do want you to know that, if you have a simple harmonic oscillator, it's going to go. Now, it's going to take a certain amount of time. So let's say I pull this thing back like this and I release it. It's going to go, and notice that from an energy point of view, the energy is either in kinetic energy or in the energy of the spring. And it's going to go back and forth, back and forth, back and forth. Well, the time it takes to make one complete oscillation is called the period. So the period, let me see that. The period is the time for one complete oscillation. So now, for this situation, we're not going to call them revolutions or rotations because it's not really rotating, is it? But it is oscillating. It's going back and forth. It's doing the same thing over and over and over again. Oscillatory. It's periodic motion. Okay. Well, what is the period of periodic motion? It's the time for one complete oscillation. And in this case, if I release it here, it's boom, and I let go of it. It's the time to come back to where it started. Well, we have this thing called, and we use the letter T. So T, and we've used T before. T is the period. Well, if I reciprocate it, I call that the frequency. Frequency, so period, let me get the units here. Period, the units are seconds per oscillation, but frequency, so frequency equals 1 over the period, and that's going to be oscillations per second. But oscillations per second is called a hertz. Sorry, I'm going so fast, but we don't have much time left. Okay. Now, that's for a complete oscillation. Remember, there are 2 pi radians in one oscillations. And yes, there are radians here, at least in terms of angular frequency and so on. We'll talk more about that later. One last thing, energy. Well, when this thing was at its pulled back like this, and I was holding it there, the energy, E, well, it's going to equal kinetic energy plus elastic potential energy. But when I have it at its amplitude, when it's all the way out here, it has no kinetic energy. All of the energy is stored in the spring. So I can say that E equals 1/2 Ka squared, where A is the amplitude. It's your value of x. It's the maximum value of x. And it's squared. Well, but if you're in the very center, E equals 1/2 mv maximum squared. Where's the maximum velocity? Well, if I pull this thing back and release it, the maximum velocity is going to happen right in the center. Or if you're somewhere in between, E equals 1/2 mv squared plus 1/2 kx squared. Now the book has allows you to take these guys here, and you can do substitutions and play around with them. But in terms of the homework problems, these are actually everything you need to know in terms of energy. The total energy is 1/2 Ka squared, the amplitude, or the 1/2 mv squared, where it's the maximum velocity. Or if you're somewhere in between the middle and the amplitude, E is equal to that. So you'll have some example problems to do and some regular problems using these ideas. That is all the time we have for this. So good luck. That is all.